Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Time Independent Fluids Flow Through Pipes. Till now what we have seen different aspects of non-Newtonian behavior and then how to measure the rheology of unknown fluid, those things we have seen. Then also we have seen a few basics of transport phenomena, and then we also derived conservation equations of mass, momentum and energy in previous lecture till now, right. So, now what we are going to do from this lecture onwards, we are going to apply those principles and then trying to obtain the transport phenomena of different types of non-Newtonian fluids. So, what we are going to start with? We are going to start with transport phenomena of time independent non-Newtonian fluids when they are flowing through pipes. So, within the category of time independent non-Newtonian fluids or generalized Newtonian fluids, we take a few cases of power law fluids and then Bingham plastic fluids, Herschel-Berkeley fluids, or even Ellis model fluids also we take, and then we are going to take a different geometries like these non-Newtonian fluids flowing through pipes, and then they are sliding down through inclined plates, etc., or between two infinite parallel plates, etc. Different types of geometries we are going to take, and then subsequent course we are going to handle the heat and mass transfer phenomena associated with these non-Newtonian fluids as well. So, we start with the case of flow of power law fluids through circular tubes due to pressure difference. That is, we have a circular tube we are having, which is having a very large L by D ratio, that is length is very large compared to the diameter of the circular tube, right. So, L by D is very large we are taking, so that we can have the fully developed flow. So, at one end we have a fluid coming in, and then at the other end fluid going out. So, what is the velocity distribution for this case, that we have to see, and then what is the volumetric flow rate, and then what is the friction factor, because now fluid has changed. So, then friction factor will also be changing. So, then what is the friction factor? So, under what range of Reynolds number the flow is going to be laminar, under what range it is going to be turbulent, all those things we are going to see one by one in coming lectures as well, right. So, let us say this is the center of the circular tube, right. Now, the coordinate system if you consider, so this is your z direction, and then this is your r direction. The radius of the circular tube is capital R, our diameter is capital D. So, now the fluid is flowing through this one because of the pressure difference. So, at z is equals to 0, what we do? We take pressure is equals to P naught, and then at z is equals to L, we are going to take pressure is equals to P L, and then the L is nothing but the length of the circular tube that we have taken, right. So, any fluid that is flowing, so now we are taking a case where there is no slip existing. So, at the wall the velocity is going to be 0, and then at the center the velocity is going to be maximum. We are taking one dimensional motion only, okay, under laminar conditions. So, those assumptions we are listing out anyway. So, then what happens, at the center you are expecting to have a kind of maximum velocity, right. So, let us say you have a Newtonian fluid. So, then what will be the velocity? Maximum velocity at the center would be 2 times to the average velocity that is flowing through. So, then as we move up, what happens? The velocity gradually decreases. The velocity gradually decreases as we move towards the wall like this, and then we have a kind of parabolic profile something like this, okay, right. So, now the velocity profile something like this, right. Gradually as you move from center to the wall, the velocity decreases, okay. Then shear stress also we have seen till now, the shear stress is 0 at the center, right. And then as we move towards the wall, it increases, and then it increases linearly for one dimensional flow in the case of a flow through circular tube like this. So, then this is the distribution of the shear stress, and then this is the distribution of the velocity. Now, the velocity here only Vz velocity is existing, one dimensional motion we are taking, the flow is predominating in the z direction. So, Vz is dominating, Vr and then V theta are they are very small compared to Vz. So, then we can take them 0. So, then this Vz velocity is function of, now what we understand, it changes with r, it is maximum at r is equals to 0, and then it is 0 at r is equals to capital R, that is at the wall, right. So, what is the shear stress that we are expecting here in this case, because one dimensional motion. So, then tau Rz we are going to have, and then that is also function of r, and then that function is a linear function that we understand through our in a capillary viscometer case also. Indeed, this is more completely same like a capillary viscometer, but the context that we are seeing is different. There the context was to obtain the shear stress, shear rate expression, so that to get the rheological behavior and then make a required adjustments because of any sources of errors, etc. Those things were the contents there. Now, here we are purely trying to find out what is the volumetric flow rate, how it is changing with respect to the pressure drop, what is the velocity distribution, how it is changing with radial position, all those things we are going to see now in this lecture, right. So, this is the physically the problem. So, then what we are going to see, we have to have a kind of enlist of restrictions of the flow, because now here we are saying the laminar flow, what are the other assumptions that we are taking. So, let us say we have taken horizontal pipe, so then gravity we cannot take, and then we are taking isothermal conditions. So, all these kind of several restrictions may also be there. So, then we are going to enlist all those things, right. So, first we do that one. So, assumptions involved in this derivation, that is derivation for the volumetric flow rate for the power law fluid flowing through a pipe, and then how that volumetric flow rate is changing with respect to the pressure difference, that is what we are going to see. So, for this derivation the assumptions are like this. So, first most important that infinitely long cylindrical tube that we are taking, so that L by D is very large, it is more than 150 or something like that. So, that end effects are not there, so that end effects etc. would not be there, right. So, then flow is laminar and incompressible, gravity is negligible, isothermal conditions we are taking, because we are not considering heat or mass transfer simultaneously along with this momentum transfer problem, we are taking only momentum transfer part. So, this isothermal conditions we are taking. Then steady state, we are taking steady state, because of the steady state dou by dou t of anything should be 0. And then what we are taking, the velocity profile is going to be symmetric. So, now this is the two dimensional view of the cylindrical tube. If you have a kind of a complete picture, so then theta d, whatever the theta is there, in the theta direction the flow is symmetric, that is what we are going to say the other one, the symmetric in theta direction. So, that is whatever the flow nature, behavior or distribution, flow distribution or velocity distribution is there between theta is equals to 0 to 180, the same that one is taking place between 180 to 360 degrees, okay. So, whatever the flow is there in the theta direction or the distribution that is there, a velocity distribution from theta direction point of view, dou by dou theta of anything is 0. That means, whatever the flow or velocity distribution is there between 0 to 180 degrees, the same thing is there between 180 to 360 degrees, right. Then fully developed flow, L by D we have taken very large, so that fully developed flow is taking place. What does mean by fully developed flow? So, let us say at this location we have a let us say this location we are calling L1. So, this is the velocity profile. Let us say you take this location is L2, again you draw the velocity profile, it would be exactly same thing whatever it was at L1. and then let us say if you draw the velocity profile at other location L3. So, then at that position also velocity profile would be exactly same like at locations L1, L2. That means along the flow direction the velocity profile does not change. So, that is the reason along the direction flow direction is z. So, here, so that is the reason dou by dou z of anything, any flow variable is 0, not kind of thing scalars or temperature, pressure kind of thing or concentration kind of thing. This is valid for only flow properties like velocity, shear stress, etc. For those things only it is valid, right. Fully developed flow, that where dou by dou z of anything is 0, that is what we are having. That is, in the flow direction velocity distribution is not going to change, okay, right. That is the another assumptions, and then this fully developed flow assumption is valid in the region away from the entry and then away from the exit, because entry and exit effects are there. So, then we are not taking the domain to get the velocity profile within this range of entry and exit. We are taking far away from entry, far away from the exit. So, somewhere in between, so that fully developed flow region is developed, in which at any location if you measure the velocity profile you are going to get the same profile. That is what mean by dou by dou z of any flow variable is 0, okay. That is the other constraint. And then flow is predominating in z direction, and then it is changing as function of r. Obviously, that is clear from the physics of the problem. So, Vz is function of r, whereas V theta and then V are very small compared to the Vz. So, then we can strike off them, we do not need to consider, right. So, now these are the assumptions. So, now what are we going to do by enlisting these assumptions? We are trying to actually what we have to do, you have to find out the so called the stress distribution and then velocity distribution, etc. for a power law fluids. Whatever I have drawn in the previous slide, that is only for the the velocity profile is only for the Newtonian fluid, right. So, it is going to be different for a power law fluid. So, how it is going to be different, that depends on the value of n, power law index. So, that we have to develop that relation, that Vz as a function of r, that we have to develop, which is again dependent on the value of n, right. So, how it is dependent, that if you wanted to find out, you have to do the momentum balance, right. So, now what we do, since this course is at advanced level course, rather doing fundamental shell balance for every problem, what we are going to do, we are going to use the conservation equation if you are solving for the momentum transfer. So, then equation of motion we use, and then we apply the constraints of the problem to simplify those conservation equations of motion. So, that you can get some kind of a simplified equation. Those equations you can solve to get the velocity profile and then shear stress distribution, etc. That is what we are going to do. Similar kind of approach we are going to follow for the heat transfer and then mass transfer problems also in the later course, in the due course of the semester, okay. So, that is what we are going to do. We are not going to do the shell balance every time as we have done in the UG course, right, because whatever the momentum equations are there, they are nothing but the momentum balance equation for a control volume, specified control volume, right. So, such momentum equations are already generalized, momentum equations are already available. So, those things we are going to use, and then we are going to apply the constraints of each and every problem that we are going to consider. So, the constraints of this problem we have enlisted in the previous slide. So, now what we are going to do, we are going to simplify the continuity equation and then momentum equations, so that to get the required velocity profile. Once you have the velocity profile, you can get anyway volumetric flow rate. So, equation of continuity in cylindrical coordinates, because we have taken circular tube, so which is a cylindrical geometry. So, then what happens, the continuity equation that we have already seen in one of the previous lecture is dou rho by dou t plus 1 by r dou by dou r of rho r v r plus 1 by r dou by dou theta of rho v theta plus dou by dou z of rho Vz is equals to 0. If the the solution, what I said, that importance of the continuity equation is that whatever the distribution, velocity distribution that you get, that must satisfy the continuity equation, right, otherwise the solution is not reliable, okay. So, now we apply the constraints. What are the constraints? We have the steady state. So, then the first term we can cancel out, and then compared to Vz, Vr and V theta are 0. So, then second third terms are also 0. Because of the symmetry also this third term is 0, anyway you can cancel out, and then because of the fully developed flow, dou by dou z of any flow variable is 0. So, that means the constraints are also consistent, and then we are getting that continuity is being satisfied here. So, this is one point of simplifying the continuity equations. In some problems what happens, you may not able to have a conclusions like whether the flow is symmetric or whether the flow is fully developed, something like that. So, then in such conditions you can simplify the continuity equation to get one of the conditions, right. Okay. So, let us say you know the flow is only symmetric, but you do not know whether the flow is fully developed or not. So, then if you simplify this equation, then whatever the condition that you get, from that you can understand. Okay. So, that is the other point of simplifying the equation of continuity, but anyway that we will do later course anyway. For this problem it is not required. Then equation of motion, cylindrical coordinates, r, theta, z components, all of them we are going to simplify. So, r component of equation of motion, this is what we have. By the way, you do not need to remember all these equations. These equations are available in standard textbooks. If at all you need to solve this problem for your assignments or for your exams, these equations would be provided. Okay. So, now for r component of momentum equation, steady state you cancel out the first term, Vr is 0, V theta is 0, V theta is 0. So, these all these terms are 0, first 4 terms now cancelled out. Vz is not 0, it is function of r, but Vr is 0. So, then that way is also it is 0, last term in the LHS cancelled out, and then because of the fully developed flow also we can cancel out the last term, right. And then pressure, in general we do not know any information about the pressure boundary conditions, pressure limitations on the pressure in general for most of the fluid flow or momentum transfer problems. So, we cannot make any judgment whether that particular term should be included or not, right. So, then we will not say anything about it, we just retain it as it is. Then only tau rz is existing here for this case, or here tau rr would function of Vr only. So, that way also it is cancelled out. Then because of symmetry this one is cancelled out, or tau theta is r also not there. So, that way also it is cancelled out. Tau theta would be having the terms of only V theta, so which is 0. So, that is cancelled out. Similarly, here because of the fully developed flow, dou by dou z of anything is 0. So, that is also cancelled out. And then we have taken a horizontal tube. So, this term is also 0, gravity we are not considering. So, what are we finding out by simplifying this r component of momentum equation? We are finding that dou p by dou r is 0, that means pressure is not function of r. Pressure is not function of r. This is what we understand by simplifying the r component equation. Depends on problem to problem. Some other geometry, some other problem, when you simplify the r component of equation, so then you may be having additional terms also, right. It is not like that every time whenever you simplify the r component of momentum equation you are going to get dou p by dou r is equals to 0. No, it is not like that. This is only for this problem, because all this cancelling out of these terms we have done based on the constraints of this particular problem that we have taken, which is nothing but the flow of a power law liquid through circular tubes because of the pressure difference. Then theta component of momentum equation, this is what we have. So, here steady state, so this term is 0, Vr is 0, V theta is 0, then Vr, V theta both are 0. Vz is not 0, but V theta is 0, as well as the fully developed flow dou by dou z of anything is 0. And then this thing we cannot say anything whether it is because pressure we do not know conditions, whether it is independent of theta or not, how it is dependent on theta, that we do not know, right. And also as I mentioned, symmetric flow conditions etc., they are for the vectors, not vectors or tensors only, that is not for the scalars. So, we cannot say this one, okay. So, just retain it as it is. And then only tau rz is existing. Tau r theta is not existing for this flow problem, it is one dimensional flow that we have taken. So, now this is cancelled out, or this tau r theta would be having the terms related to the V theta and then Vr, V theta function of r, Vr function of theta, maybe we are having right. Vr and v theta terms may be there, Vr function of theta and then v theta function of r may be there. So, both Vr v theta 0, so then this should also be 0, and then the same way this is also 0 because the otherwise because of the symmetry also this is 0. This is not there, tau theta z is not existing, or because of fully developed flow also dou by dou z of anything is 0. And then for symmetric laminar flow, these two quantities are going to be same. So, then the difference is going to be 0 anyway. We are not considering gravity in this problem. So, then what we understand from here, dou p by dou theta is equals to 0, that means pressure is not function of theta also. So, now by solving this r and theta components of momentum equation, what we understand, pressure is not function of r and theta. In fact, we do not need to worry about this one also, because it is already given in the problem statement. The flow is because of the pressure difference, and then pressure difference is in the z direction. At z is equals to 0, pressure is equals to P naught, at z is equals to L, the pressure is equals to PL. Okay. So, that is what we have anyway. Then z component of momentum equation, if you simplify. So, this is the equation. So, steady state this term is 0, Vr is 0, V theta is 0, Vz is not 0, but dou by dou z of any flow variable is 0 because of the fully developed flow. So, left hand side all the terms are cancelled out. Dou p by dou z, we cannot say the pressure, right. So, whatever the fully developed flow condition etc. is there, that is also for flow variables, not for the scalars like temperature and pressure. So, then we cannot cancel out this one, right. And then tau rz is existing because it is having Vz, and then Vz is function of r. So, we cannot cancel out. So, then this term would be there, and then tau theta z is not existing because it will be having V theta Vz. Vz is function of r only, it is not function of theta. So, that way also this term is cancelled out, or it will be 0, or because of the symmetry also this term is 0. Then because of the fully developed flow, dou by dou z of any flow variable, tau z is flow variable, it is not scalar. So, then that is cancelled out, and then we are not taking gravity. So, that is cancelled out. So, only these two terms are remaining. That means, dou p by dou z is equals to 1 by r, dou by dou r tau rz. So, this equation we can solve. So, now what we understand now here, pressure is function of z. Pressure is function of z, it is already clear from the previous two simplifications also, but now the same thing is realized here also. Pressure is function of z, right. So, now further these momentum equations we are simplifying for a Cauchy's momentum equations we are simplifying. We are not simplifying Navier-Stokes equations. Navier-Stokes equations are explicitly for Newtonian fluids, right. Cauchy's momentum equations are generalized for any fluid, Newtonian or non-Newtonian fluid. Only that in the place of tau, if you substitute respective equation for the nature of the fluid or rheology of fluid, so then that equation would be for that fluid. Okay, right. So, now this equation if you solve, then you can get expression for tau rz, and then after that you further simplify this one depending on the nature of the fluid, Newtonian or power law or Bingham plastic anything, then from here you can get the velocity profile Vz. Okay. How, that we are going to see now. So, this is what we get. What we understand by simplifying r and theta momentum equation, P is not function of r and theta, right. So, left hand side it is dou p by dou z, it is function of z only, but right hand side we are having all out of r theta z only r variable coordinates are there here, right. So, only r coordinates are there. So, then for left hand side term, the right hand side term is nothing but is a constant time kind of thing, because left hand side term, the pressure term is there, that we already realized that it is independent of r. So, that is the point of simplifying all equations of motion. So, you get certain information definitely which is going to be useful, right. So, now we understand only it is only function of z from this z component of momentum equation. So, right hand side term it is all function of r. So, then for left hand side term, the right hand side term is a constant. Similarly, right hand side term, it is all function of r, and then tau rz, it is having vz, and then it is function of r only, it is not function of z. So, for the right hand side term, the left hand side term, whatever dou p by dou z term, dou p by dou z is there, that is constant. That means we can integrate this equation independent of each other and then get the solution. Okay. So, that is what we are going to do, right. So, because of this nature, we can also write this equation in ordinary derivatives like this, dp by dz is equals to 1 by r d by dr of r tau rz. Now, we can integrate this dp by dz because it is function of z only, and then RHS is independent of z. So, then when you solve this dp by dz is equals to some constant c naught, then you when you take this dp by dz is equals to some constant c1. So, then you get p is equals to c1z plus c naught. So, that is what you have. What is this constant c1? Let us not worry about it. Okay. Right. So, that is what we have. So, now for this you apply the boundary condition and get the pressure distribution, whether it is linear or non-linear in the z direction, that is what you get. So, at z is equals to 0, we got p is equals to p naught. So, that if you substitute you get c naught is equals to p naught, one constant you got. At z is equals to L, pressure is nothing but PL, that is given schematically, that in the first slide we had. So, that means PL is equals to C1L plus C naught. So, C naught you already got P naught, then C1 is nothing but from this equation PL minus P naught by L. So, now you got both C naught and then C1 expression. So, that you substitute here in this equation, so that you get this expression, P is equals to minus of P naught minus PL by L Z plus P naught. This is what you get. This is nothing but you can take it as minus delta P by L. Okay. So, what you understand from here? You understand that pressure is a linear function of z. It is function of z, but this function is a linear function, that is what you understand. Okay. Or dou p by dou z is equals to minus delta p by L, that is what you get from this equation. So, this is going to be useful anyway, right. So, now in the equation number 1, what we have? 1 by r dou by dou r of r tau r z is equals to dou p by dou z. Now, dou p by dou z is nothing but C1 that we already got, which is nothing but minus delta p by L, right. So, this is minus delta p by L. So, now this equation you can integrate, So, when that you do it, you get d by dr of r tau r z is equals to r dp by dz, that means r tau r z is equals to r square by 2 dp by dz. dp by dz we are not substituting, we can substitute later on, no, there is no issue at all, plus integration constant C2. So, then what you get? Tau r z is equals to r by 2 dp by dz plus C2 by r, right. Now, this r is varying between 0 to capital R, right. So, if r is equals to 0, so then what happens? This constant by 0, it's not going to be defined, it's going to be infinite, right. So, that is not possible. Shear stress, that cannot be infinite because of the continuum hypothesis. No flow variable or physical properties can be infinite or undefined at any location. That is what we have seen one of the previous lectures. So, that means this C2 has to be 0. Then what you get? Tau r z is equals to r by 2 dp by dz, and then dp by dz is nothing but minus delta p by L, that is tau r z is equals to minus of minus delta p by L r by 2. This is what you get, right. So, the same thing you can write, tau r z is equals to minus delta p by L r by 2. Right. This is the shear stress distribution, and then what we understand, delta p by L is constant. So, what we understand, the shear stress is linearly changing with r location. It is 0 at the center and then it is maximum at r is equals to capital R. That is what we can understand from this equation number 3. So, what is that maximum value of shear stress? If you substitute r is equals to capital R, then you get that maximum value of shear stress, that is nothing but the wall shear stress, right. So, that is tau w is equals to minus delta p by L capital R by 2, right. So, you got the shear stress distribution, but your interest is not just a shear stress distribution, it is also to get the velocity distribution and then subsequently finding out the volumetric flow rate. So, for power law fluids, what is tau Rz? Is nothing but m minus dVz by dr power n, minus we have minus dVz by dr we have taken, because what happens, the pipe or circular tube whatever we have taken, the velocity is maximum at the center, right, and then it is decreasing as we move towards the wall from r is equals to 0 to r is equals to capital R. So, that means as r increasing, the velocity is decreasing. So, then this gradient, velocity gradient is going to be negative. That is the reason we have to take minus here. This whether should you take minus or plus, that depends on the flow geometry like this. Okay. So, tau Rz is equals to m minus dVz by dr power n is the expression for power law fluids. Okay. The relation between shear stress and shear rate for power law fluids is given by this equation. This we have seen in the introduction of non-Newtonian fluids, right. So, then this equation tau Rz, just now you got it as minus delta p by L R by 2. So, then that we have written here. So, next step what we are going to do, we are taking this m to the right hand side, and then both sides we are taking power 1 by n. So, that we get minus dVz by dr is equals to minus delta p by 2 L m whole power 1 by n r power 1 by n, this is what you are going to have. So, this expression also we are this is nothing but the variation of the shear rate, how the shear rate is varying with r, because this now this parenthesis whatever the term is there, this entire thing is constant for a given fluid, for a given power law fluid of known m and n value, this is a constant. So, it is shear rate is changing as a r power 1 by n, r power 1 by n it is changing. Okay. So, now this is we are going to use later also in for other purpose of simplifications, right. However, first what we have to do now, we have to integrate this equation to get the Vz, that we can do it when you do minus Vz is equals to, this is all constant, and then integration of r power 1 by n is nothing but r power 1 by n plus 1 divided by 1 by n plus 1 plus integration constant C3. Now, the velocity at r is equals to capital R is 0, right. So, that boundary condition if you use, then you get C3. So, at r is equals to capital R, Vz is 0. So, C3 should be whatever this term is there minus of this term capital R power 1 by n plus 1 divided by 1 by n plus 1, that is what you get. So, this is the C3. Now, this C3 you are going to substitute in the minus Vz is equals to this particular term, and then plus C3 was there, in place of plus C3 this is the term that we got, right. So, now here what we do, except this this equation we rearrange such a way that we have minus Vz one side and then minus whatever this square parenthesis terms are there, that we are taking common, and then also we are taking r power n plus 1 by n also common from the both the terms, from these two terms. So, out of that r power 1 by n we are combining with this minus delta p by 2 Lm whole power 1 by n term. So, that we can have minus delta p by 2 Lm capital R whole power 1 by n, and then remaining r we are writing here. So, that this is what we are having. So, this is minus Vz. So, then plus Vz would be this particular term here. So, this would be 1 minus r by r whole power n plus 1 by n, it will be there. What we have seen, minus delta p by L capital R by 2 is nothing but tau w. It is nothing but tau w, in the previous slide only we have seen, right. So, that is what we have seen. So, in place of minus delta p by L, capital R by 2, I have written tau w divided by m is as it is whole power 1 by n, and then n r by n plus 1 multiplied by 1 minus r by r whole power n plus 1 by n. So, for shear thinning fluid, if you substitute n less than 1, whatever the n value is there, so then you get the velocity profile for shear thinning fluids flowing through pipes, right, circular tubes or pipes, right. If you shear thickening fluids, if you substitute n greater than 1, so then you get the velocity profile for that fluid flowing through a pipe. So, that you can understand, you can calculate from this one. So, you can use this equation either in terms of minus delta p by L, or you can use the tau w terms as well, anyway you can write. Okay. So, now volumetric flow rate, if you wanted to find out, you can do it integral 0 to 2 pi 0 to r Vz r dr d theta simply, because Vz is now known, Vz as function of r is known. So, it is not function of theta. So, then that we can write 2 pi integral 0 to r Vz r dr we can write, right. So, that we have written here, and then further what we are doing, we are r we are writing r by capital R. So, that d also we can dr also we can write d r by capital R. So, we are dividing by r square here. So, then we have to multiply by r square here. Why are we doing? Because Vz is having something like terms r by r. So, then if you do the integration with respect to r by r, it will be easier. Otherwise, there is no particular reason that writing in this form. So, Vz just now we have seen tau w by m whole power 1 by n, n r by n plus 1 multiplied by 1 minus r by r whole power n plus 1 by n, r by r, dr by r is as it is here. Okay. So, this term is nothing but your Vz terms. Integration you are taking changing from r to r by r. So, then obviously these limits also will change from 0 to 1, because at r is equals to 0, r by r is also going to be 0, at r is equals to capital R, r by r is going to be 1, right. So, now what we do, we multiply this r by r or bring this r by r inside this parenthesis, and then we are going to do the integration. So, when you do it, so because all these things are constant, so then we can take out as a common outside of the integration. So, we have the integration r by r whole square divided by 2 minus r by r whole power 2n plus 1 by n plus 1, that is 3n plus 1 by n divided by 3n plus 1, and then 0 to 1 are the limits. When you substitute 0 to 1, when r by r is 0, so then lower limit both these terms are 0, upper limits when you substitute 1 by 2 minus 1 by 3n plus 1 by n, that is n by 3n plus 1, that is what you get. So, 1 by 2 minus n by 3n plus 1 you get, remaining all other terms are constant. Now, this you can do LCM further simplify to get this q value as this one. So, this n plus 1 also you can cancel out. So, this is the final volumetric flow rate. This you can write in terms of tau w, as well as you can write in place of tau w you can write minus delta p by L capital R by 2. So, that you can write this equation as like this, fine. So, now here we are combining all the terms. So, then we have n pi r cube by 3n plus 1 multiplied by minus delta p by L capital R by 2 m whole power 1 by n is volumetric flow rate, right. So, now you have a Vz expression, you have a Q expression, you have a tau Rz expression also, you got it, right. So, further what we are going to do, we are getting minus dVz by dr, how much it is. So, that to get shear rate also, and then shear rate also we will be representing in terms of Q, and then after that we will be doing the simplification, what is the maximum velocity, average velocity, etc. So, as I already mentioned at the beginning, this equation that we have already derived, that is we are going to reuse somewhere later. So, this is the point, we wanted to find out the shear rate as function of Q. So, now this is what we have already seen one of the previous slides. Now, in this just now previous slide Q we got this expression equation number 6, right. So, now here what you do, wherever this minus delta P by L capital R by 2 m whole power 1 by n is there, in that place in this equation you can write Q multiplied by 3n plus 1 by n R cube by n, that is what you can write, and then divided by this whatever this R is there, no, this R power 1 by n, that is here, and then small r power 1 by n is as it is here. So, that is what we are doing. So, simply this equation number 6 we are using in this above equation here, so that minus dVz by dr we can represent in terms of volumetric flow rate. That is the thing that we are doing, because in general you know the volumetric flow rate. So, then that directly you can substitute and get the shear rate information. So, at the wall if you wanted to know the shear rate, what you have to substitute? You have to substitute R is equals to capital R. So, that you substitute. So, then capital R power 1 by n divided by capital R power 1 by n you get. So, then both are same. So, you have wall shear rate is nothing but 3n plus 1 q by n pi r cube. So, then this equation what you do, you multiply by 4 and divide by 4, so that you can write 4 q by pi r cube multiplied by 3n plus 1 by 4n. This is how you can write the wall shear rate. Okay. So, now you got the shear rate expression also in addition to the shear stress. Now, what we got till now? We got the velocity distribution, volumetric flow rate expression, shear stress distribution, shear rate distribution, etc. all those things we have seen. So, now what we are going to do here? We are going to plot the velocity distribution, because if a Newtonian fluid is flowing through infinitely long circular cylinder, we know that velocity profile in the fully developed flow region is a parabolic profile. Is it the same for fluids like shear thinning fluids, or the different flow rate or the different distribution is going to be there? That is what we are going to see now here, right. So, this Vz we have already derived, where tau w is nothing but minus delta P by L capital R by 2. So, in terms of minus delta P by L, if you wanted to write the same expression, you can write like this. Okay. Now, average velocity if you wanted to find out, you have to divide the volumetric flow rate by cross section area of the pipe through which the fluid is flowing. So, then Q divided by pi r square, if you do, you get the V average. So, that is Q, just now we got this expression, equation number 6. If you divide this one by pi r square and then do the simplification, V average you get n r by 3 n plus 1 multiplied by minus delta P by L r by 2 m whole power 1 by n. This is what we have, right. So, rewriting that equation number 8, that is for the velocity distribution in terms of minus delta P by L and r. Then V average, just now we got this expression. So, then when you do Vz by V average, so then what will happen? So, these term are same, right. So, then remaining terms if you rearrange, you get Vz by V average is nothing but 3 n plus 1 by n plus 1 multiplied by 1 minus r by r whole power n plus 1 by n, that is what you get, right. So, this expression we are going to use it now. Anyway, that is average velocity. If you wanted to find out the maximum velocity, velocity is going to be maximum at the center of the circular pipe that we have taken. So, then we have to substitute in the velocity profile distribution r is equals to 0. In the velocity profile distribution equation whatever we derived, that is equation number 8, if you substitute r is equals to 0, then you get maximum velocity. If r is equals to 0, so then this term is 0, right. So, that means V max you are going to have minus delta P r by 2 Lm whole power 1 by m whole power 1 by n, n r by n plus 1, that is what you are going to have. So, now Vz by V average, we already got it in the previous slide. This is what we got. Now, if you wanted to find out V max by V average, what you have to do? V max by V average, if you wanted to find out, in this equation number 10, if you substitute it R is equals to 0, then you get V max by V average, right. Then you get V max by V average is nothing but 3n plus 1 by n plus 1. So, let us say if it is Newtonian fluid, n should be equals to 1, that means V max by V average is equals to 2, that we already know, right. So, that is what we get, V max by V average is equals to 2 for the Newtonian fluid, but it is not equals to 2 for shear thinning or shear thickening fluid, it is different, depends on the n value. So, that means velocity profile is going to be different for shear thinning or shear thickening fluid. We are not going to get parabolic profile as well for the shear thinning and shear thickening fluid flowing through pipes, that we get parabolic profile we get only for Newtonian fluids. So, how do the profile look like for shear thinning and shear thickening fluid, that is what we have to see now. So, this is what we are taking. So, for that we are plotting R by R versus Vz by V average. So, Vz by V average, that equation number 10 just now we had, that is Vz by V average we had 3n plus 1 by n plus 1 multiplied by 1 minus R by R whole power n plus 1 by n. Now, what you do? You take different values of n, different values of n you take n is equals to 1, you take n is equals to 3, then you take n is equals to 1 by 3 also. So, this is shear thinning, this is Newtonian, this is shear thickening, and then you take different R by R values between 0 to 1, because R by R it is the radial coordinate is divided by the radius of the tube. So, then maximum value of R by R is going to be 1 only. So, between 0 to 1 you take different values of R by R for each n value, and then you find out the values and then tabulate them, then you plot them. So, what you get here. Let us say if R is equals to 0, or if R by R is equals to 0 and then n is equals to 1, n is equals to 1, R by R is equals to 0, that means this Vz by V average here, if it is 0, so then we are going to get 3n plus 1 by n plus 1 only, n is equals to 1, so then 4 by 2 is 2. So, n is equals to 1 when R by R is equals to 0, Vz by V average is 2, so that data point is here. Fine. So, now what you do? You take R by R is equals to 0.4, then Vz by V average you find out how much it is. It will be roughly 1.75. So, that data point is here, right. So, next what you do, like that you keep changing the data points. Let us say you take the R by R is equals to 0.7 or something like that, then so when R by R is equals to 0.4, Vz by V average for Newtonian case we are getting something roughly like 1.75 or 1.8, something like roughly. So, that point is this one. Similarly, if you take R by R is equals to something around 0.7, then Vz by V average you will get approximately value of 1. So, these are approximate values that I am saying. So, then that data point would be here. So, like that you take different data points and you plot. So, then what you find? You find for the Newtonian case you are going to get a parabolic profile like this, right. So, let us say if you have n is equals to 1 by 3, then R by R is equals to 0, then what is your Vz by V average? So, R by R is 0, so then this term is 0. If n by 3, if n is equals to 1 by 3, so this is how much? 1 by 3 into 3, that is 1 plus 1, that is 2, 2 divided by this is 4 by 3, that is 488 divided by, so that is you get roughly you are going to get that value close to 1.5. So, that is the data point here, right. Likewise, if you change the R by R value to 0.4 here in next level, then this Vz by V average you are going to get roughly something like 1.4 or something like that. So, that data point is here. So, like that if you plot, so for n is equals to 1 by 3 you are going to get a flatter profile like this curve. That means for Newtonian fluids it is a parabolic profile, but for shear thinning fluid it is a flatter kind of profile you can get here. This profile you can see, this is a flatter kind of profile you can get. And then similarly, if you do for shear thickening fluid, let us say if you take n is equals to 3, then at R by R is equals to 0, Vz by V average you are going to get 2.5, that data point is here. So, likewise other cases also R by R if you take, and then for n is equals to 3, if you obtain the data points and then plot them together here. So, you are going to get a steeper profile like this. So, shear thickening fluid profile is sharper, and then as n increases it becomes very sharper. So, the velocity profile of a shear thinning fluid flowing through a pipe, if the flow is fully developed flow, the velocity profile is going to be flatter one, and then as n increases it flatness gradually decreases, and then for n is equals to 1 the profile becomes parabolic, and then further if you increase n value where shear thickening behavior started n greater than 1, then the profile becomes gradually sharper, and then n is equals to infinity it becomes straight lines like this, straight line profile like this you can get here as shown here. Okay. So, now we realize that if the fluid rheology changes, the velocity profile is going to be very different. So, then obviously the volumetric flow rates are also going to be different, or for a fixed volumetric flow rate of Newtonian fluid, whatever the pressure drop is there, the same pressure drop may not be giving the same volumetric flow rate if the fluid is a non-Newtonian shear thinning or shear thickening fluid. We are going to see with an example problem also. So, from equation number 12, this is what we get, V max by V average equals to 3 n plus 1 by n plus 1. That means, maximum velocity as n decreases from 2 to 0.1, the maximum velocity drops from 2.33 average to 1.18 V average velocity. So, when n decreases from 2 to 0.1, V max velocity decreases from 2.33 times V average to 1.18 times V average velocity. Okay. So, that much important is the rheological nature of the fluid to be considered while designing any unit operation where the non-Newtonian fluids are being handled, or even for the tuning the operational parameter as well. Okay. So, center line velocity for Newtonian fluids is nothing but 2 times the average velocity that we have seen anyway. So, now we see a few more details, because whatever the volumetric flow rate versus delta P, that is important from engineering applications point of view. That information now we are going to analyze for power law fluids here in this case. Volumetric flow rate, we got this expression previously in one of the slides we have derived it. This equation I am rearranging this way, that is it, doing nothing, we are just rearranging so that all the R terms are grouped together. So, that for a fixed value of R, how the Q is changing for a change in delta P, that is what we are going to see. How it is changing? Q is proportional to minus delta P power 1 by n, or minus delta P is proportional to Q power n, that is what we are getting here, right. So, for a given power law fluid and fixed pipe radius, minus delta P is proportional to Q power n. That means, for a shear thinning fluid, the pressure gradient is less sensitive than for Newtonian fluid to changes in flow rate. That is what we can understand, because n is less than 1. So, then this the pressure drop would be less sensitive compared to the case when n is equals to 1. That is what we can understand. The same equation 13 again. So, now let us say for a fixed pressure drop, if the pressure drop if you are keeping fixed, then Q is proportional to R power 3 n plus 1 by n. That means, flow rate shows a strong dependence on radius of pipe for shear thinning fluid. For shear thinning fluid, the flow rate shows a less dependence on the pressure drop, but it shows a strong dependence on the radius of the pipe, because it is for a fixed pressure drop Q is proportional to R power 3 n plus 1 by n, whereas for a fixed R value Q is just delta P is just proportional to Q power n only. So, the flow rate is strongly dependent on the radius of pipe for shear thinning fluid rather than the pressure drop. That is what we can understand here. So, for n is equals to 1, that is Q is proportional to R power n, whereas for n is equals to 0.5, Q is proportional to R power 5. That is what we have here. So, the radius of pipe is going to have more influence on the flow rate for the case of shear thinning fluids. So, before winding up this class, we will take a simple example problem. So, there is a polymer solution of certain density is being pumped at a certain mass rate through a pipe of certain diameter, and then flow is known to be laminar and power law, and the power law constant for this fluid, whatever the power law fluid is there, that rheology is represented by the power law of nature. So, then m is 3 Pascal second power n and n is 0.5. So, the question is, estimate the pressure drop over a 10 meter length of straight pipe and the center line velocity for these conditions, that is minus delta P and V max we have to find out. The second part of the question, how does the value of pressure drop change if pipe of 37 mm diameter is used to maintain the same flow rate? If you maintain Q same and then you increase the diameter of the pipe, how much pressure drop is going to change? That is the second part. Very simple straightforward calculations. Actually, Q versus minus delta P, that relation we have already developed. So, Q is given, actually m dot is given, density is also given. So, m dot by density if you do, you get the Q value, that Q is nothing but this value, 2500 kg per hour. So, per hour we have written 3600 seconds and then dividing by density 1075 kg per meter cube. So, then volumetric flow rate you get 6.46 multiplied by 10 power minus 4 meter cube per second. And then R is given as 25 by 2 mm, that is 0.0125 meters. And this equation 13, we derived this equation just now in one of the previous slides. So, in this equation except the minus delta P, everything is known. So, you substitute all the values capital R, N, M, L, Q in above equation, because N and M also given in the problem. Then you simplify, so you get minus delta P is nothing but 110 kilopascals, right. And then average velocity, Q is already obtained. So, this Q if you divide by pi r square, then you get the average velocity 1.32 meter per second. It is not part of the question, but we can do anyway. Then maximum velocity is nothing but 3 n plus 1 by n plus 1 times the average velocity that we have already seen. So, that you substitute n here, V average you got 1.32 meter per second here. So, then 2.2 meter per second. So, the pressure drop as well as the center line velocity or the maximum velocity we got. The first part is done, right. Now, second part is that if you change the diameter of the pipe, it is rather increase, so then how the pressure drop is going to change. So then same equation number 13 we are using it here. So between Q versus R, what is the relation? Q is proportional to R power 3 n plus 1 by n, that is what we have, right. We are having constant flow rate. Okay. So otherwise what we get from here, minus delta P whole power 1 by n is proportional to R power minus 3 n plus 1 by n. This is what you have. R minus delta P is proportional to R power minus 3 n plus 1 you are having. Why are we getting this relation? Is because if your radius is changing, you know how much pressure drop is changing, that is what you wanted to find out. Though the same equation you can use as it is by substituting R is equals to 37 by 2 multiplied by 10 power minus 3 meters directly, but we do this way. So for pipe diameter of 37 mm, minus delta P nu, that is for D is equals to 37 mm divided by that should be equals to whatever the minus delta P old, which is nothing for D is equals to 25 mm, and then that should be multiplied by R nu by R old whole power minus 3 n plus 1. Nu stands for the case of 37 mm diameter, old stands for the case of 25 mm diameter. So 25 mm diameter, delta P old we already calculated previous slide, 110 kilopascals, that you substitute. R new, R old are known, right. Then delta P new. So that is for the case of that is for the case of diameter of 37 mm pipe, minus delta P is going to be 41.3 kilopascals. So it has decreased substantially by increasing the radius of the pipe. This is the second part of the problem. One last addition, let us say if the fluid is Newtonian, then n should be equals to 1, and then whatever the m value is there, that should be taken as mu, right. Then you get minus delta P nu, you are going to get, if you use the same equation, this equation, just n is equals to 1 you substitute, and then m is equals to you substitute 3, and then do the simplification, you get 23 kilopascals, which is almost half of this value, right. That means higher pump energy is required to maintain same flow rate of shear thinning fluid as compared to the case of Newtonian fluid. So whatever the volumetric flow rate, that 6.46 into 10 power minus 4 meter cube per second, that volumetric flow rate that is given here, that means you are using 37 mm diameter pipe, and then in order to maintain 2500 kg per hour of mass rate, what is the pressure drop for a Newtonian fluid is just 23 kilopascals, 23 kilopascals. But if you maintain the same flow rate for a shear thinning fluid of n is equals to 0.5 and then m is equals to 3 pascal second, then it increases to 41, roughly 41 kilopascals, right. So that is what, to maintain the same flow rate you need to provide the higher pump energy in the case of shear thinning fluids compared to the case of Newtonian fluids. So the references for this lecture, the entire lecture is prepared from this reference book by Chabra and Richardson. Other reference books are provided here. Thank you.